Hello, 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 chemists, and welcome to Tuesday. This is going to be your practice day for Boyle's Law. You already got some stuff to look at yesterday. Today we're going to be posting the keys, as well as another sheet of practice if you'd like it. So I'd like to remind you all that practice makes perfect. Oh, oops. Sorry, let me fix that. Okay, practice makes perfect. And I hope you'll excuse my dumb joke, because that's kind of the point of today, and you also get another practice day later in the week. But these questions have some little curveballs, they have some little, twists, and I'm going to show you two examples today, just pretty briefly, to get you all geared up to keep doing the practice sheets. And the more you do of those, the more routine they'll become, and the better you'll feel. So, with that in mind, let's read a question. Here it says a container with 4.34 liters of gas at 2.53 atmospheres is moved to a new container with 6.54 liters of space. What's the new pressure? So before I give you a chance to actually start on this, I want to draw your attention to this equation. This is the Boyle's Law equation, and it's what you're going to be using for, I guess, all of these, all the ones in your practice and for your reasoning and such. Remember from our lesson yesterday, which if you haven't seen, go back to yesterday's video and watch the lesson itself, because that'll help you a lot to get started. But this is saying that if we increase the pressure or something, then the volume will go down, or if we increase the volume, the pressure goes down with gases. So I'd like to invite you on both of these examples to pause the video and work ahead, because you should have been already trying these and have some idea of how to proceed. So I have also posted a work key for the booklet thing, which you can check your work on. But alongside these, it's helpful if you try them on your own piece of paper or on your calculators and such. And then I'll resume and you can see if you did it right or if you went wrong in a little tiny place that you can fix. Um, yeah, so with that in mind, I'll start going through the steps in about 5, 4, 3, 2, and here we go. So this is how we're going to pull out the information from the question to set it up. We start at 2.53 atmospheres, that's our P1, our first pressure. We're at 4.34 liters, which is our first volume, V1, and that equals P2, which is what we're looking for. So we don't have any number to put there yet, that's what we'll solve for. And we know that we're going to end up with 6.54 liters of space, that's our V2. Then we can just rearrange this by dividing by 6.54 on either side. Just algebra stuff now. So we're going to divide by 6.54 and that'll give you a value for P2. I'm going to invite you now to type this into your calculator before I go on, because a lot of this is just making sure you get your calculator steps right after you've set it up correctly. And that'll be like multiplying here and dividing by 6.54. Coming off of stoichiometry, you should all be pretty used to typing fractions and big numbers and dividing and multiplying lots of even crazier numbers than this, so this shouldn't be terrible. But I'd like you all to do a little calculator check right now to make sure you get the same value that I have, and I'm going to type it in as well. So pause the video, or just do this alongside me. We're going to go 2.53 times 4.34, and then we're going to divide that all by 6.54, and these units are going to cancel, so we're going to be left with a value in atmosphere. In 3 seconds, I'm going to show the answer, so make sure you're ready. 3, 2, 1. We'll be left with 1.68 atmospheres, ATM, as the second pressure, and that would be your final answer. Stay with me here, though, because we're going to do another example with a little twist in one moment. But feel free to pause the video, take a photo of this, make sure you got it lined up, and yeah. Moving on. We're only going to do 2 examples in this video because they all follow a similar skeleton. This next example has a little twist that you are going to run into. So here you go. A container is at 556 millimeters of mercury, which is the same as torr, just FYI, pressure, and the pressure is lowered to 54.2 kilopascals at a volume of 456 milliliters. What then was the starting volume? I like my commas there, that's really fancy. But you're going to notice something different here. See if you can spot it before I give it away, but there's something here that we need to address before we can really get going. Take a second, investigate, and see what you come up with. I'm still here, I'll be back in a couple seconds, but just keep looking, pause the video if you want, and see what's going on here, which is a bit different than what we are used to. Okay, so this is our equation once again. P1V1 equals P2V2. P2V2 sounds like R2D2's cousin or something. Anyways, the thing with this is it's like a proportional equation. We're looking at like a ratio. Remember that Boyle thing where we made the graph that went up inversely? If we're comparing a pressure to a pressure, or a volume to a volume, we have to make sure they're in the same unit. Remember our standard units, right? Where it's like 760 millimeters of mercury is like 1 atmosphere. So if you have 760 on this side and 1 on the other, it's going to change your answers tremendously, even though it's the same pressure. So we have to make sure that we keep, whenever we're setting this up, we'd have to have, it doesn't matter which one, but as long as they're the same, so we'd have to have millimeters of mercury and millimeters of mercury, or kPa and kPa, liters and liters, not like milliliters and liters. We just have to make sure the units on one side are the same as the units on the other. So here we have 556 millimeters of mercury given. I'm just going to change that to kPa. You could also change kPa to millimeters of mercury. It doesn't matter as long as they end up the same when you're working through the equation. But for example here, 556 millimeters of mercury, we're going to set up our conversion factor, 101.3 kPa per 760 millimeters of mercury. This is the stuff from last week, so remember, all the stuff in chem doesn't go away. You got to keep it in the back of your mind like a little tool chest. And we're going to use that. So here's our conversion factor, canceling units. Oh, that's supposed to be down there. Just don't worry about that. But we're going to cancel out the millimeters of mercury, pretend that's the thing getting chopped off. And we get left with 74.1 kPa. That was just 556 times 101.3 divided by 760. And that's your last week unit on gas unit conversions. So with that done, we can set up our actual equation. So I'm going to invite you to set up this equation and see what you can get as a final answer. Then I'm going to pick back up in a few moments here. And yeah, we'll see how that all went. So I'll give you 5, 4, 3, 2, 1, and that's how we're setting it up. Here we're looking for V1, so it's a bit different than the last one. 74.1 kPa is our starting pressure. It's the same as 556 millimeters of mercury, but we had to convert it so it was the same on both sides of the equation. So that's our starting pressure that we worked out here. We're looking for V1, so that's just going to stay as our variable. Then we have 54.2 kPa at a volume of 456 milliliters as our final conditions. So then we can divide by 74.1 on either side to end up with this as our final thing to plug in. And again, I'm going to invite you all to take a moment and type this into your calculator. Pause the video before I move ahead to make sure you're typing these in as proper. And see what you come up with. So we're going to go 54.2 times 456, all divided by 74.1. And we get, ready? Okay. We cancel those units and we get V1 equals 334 milliliters. I rounded this up. You might have 333 depending on your rounding before, but as long as it's ballpark there. Again, stakes matter, but they're not the total focus right now. I want you to get used to using these equations, so keep it reasonable. But anyways, with those examples in mind, you should be able to tackle all the problems given to you today for Tuesday, and then be ready for a little twist and a new topic tomorrow for Wednesday. So anyways, chemists, I wish you the best of luck, and I hope you have a lovely day. Thanks.